today we're going to have a very interesting talk about inductive biases, that you can get from logical constraints. And I'm looking forward to this. You can find out more about Nijesh's work here. If you want. You can also put this in Discord. Okay, so find out more about Nijesh's work here. And you can ask questions in any of these three places. And with that, and one more thing, next week, we're going to stop soon. We're going to have a pause on talks about a month before the summer school, but we have a few more great talks, and one of them, the next one is this one. All right, by Dylan. And with that, Nijesh, take it away.
Awesome.
Yeah.
Okay, so first of all, let me thank Olga, Alex, and Joe, and Centaur Institute in general for having me for this invited talk. It's a pleasure to be here. I'm joining from Edinburgh, and I'm being supervised by Vaishak Bell. And today I'm going to walk you through logical constraints as inductive biases in learning and generation. Previously, I was instead going to talk about LTN-GAN as the major work, but then I realized that having these two contrasted together would give a better perspective to the audience here. So let me start with a tale of two papers, right? So then here, the talk is built around two pieces of work. On the left, you see a learning problem where you can imagine you see two handwritten digits and you are told only that they sum to 5, and you never know what those individual digits are, right? And how do you, come up with a model that recover the digit, the individual digits from here? This is part of the Royal Society work, which is to, due come out soon. And then on the right, you have the generation problem where you have a standard GAN, and how do you get the GAN to respect exact domain rules so that it is able to do better than what it usually does. So essentially like constrained GAN, right? But using LTN as the framework. This was part of the ICLP 2025 work, but the archive links are here. Now, just to give a little background on how neuro-symbolic AI essentially works is we have these two paradigms, symbolism and connectionism. And this is kind of the holy grail the Institute was started with. So maybe not too much, I need to save some time here to walk through other aspects, but just a quick kind of thing as to say that there's two different strands in AI, symbolism and connectionism, and our goal is to fuse them together. And then now here we're looking into logic as an inductive bias. Right. So an inductive bias in this case is just a preference for some solutions when the data alone does not decide. Right. Usually, this sort of bias comes from the architectural, convolutional, or attention-related aspects of things. But here it is the logical constraint, and it shows up in two different ways. On the learning side, logic is a restriction. So we're trying to essentially restrict the hypothesis space within which we search on. And then the regularization, logic is a loss. So we essentially input the logic into the loss function and see what happens. But we'll get into the details into this in the following slides. Now, just as a quick overview, which is kind of maybe redundant at this point, is that logic constraint is an inductive bias. That is what we want to take away from this. Could act as a bias. So let me quickly dive into weak supervision setup. Weak supervision means learning from labels that are limited, noisy, or ambiguous. And it is attractive because such labels are cheap and plentiful, and also can be achieved and can also be gained at scale. And it can, but the problem here, pins down to the aspect of trust, right? When a model trained this way works, we usually cannot say why and when it will fail. So in high-stakes settings, where let's think about health or law or sciences. We need reliability and clear semantics. So in that setup, the high accuracy number means not much to us, right? We want the systems to be reliable and clear and interpretable to our own sake. So essentially here, can we give weak supervision a logical semantics of some sort, using which a precise account of what, which label assignments are consistent with the supervision can be known, and then there's also a way to diagnose if there's failure in some cases. So within weak supervision too, there's multiple different strands. Within that, we just focus on the inexact supervision, within which MIPLL, the multi-instance partial label learning, becomes the kind of the problem space we operate on, the setting. So MIPLL combines two kinds of weaknesses as once, right? So we have the multi-instance setup, where you are given a bag of instances and not the single labeled examples, and the partial labels, where you'll see one aggregate label for the whole bag, and the per instance labels are latent. They're kind of hidden from the view. So going back to the 2+3 sum example we had before, we have the sum label as 5, but we do not know that the individual digits are themselves labeled as 2 and 3. So it could be multiple different combinations of those. So just to zoom into the problem a bit more and to give you a lens into what this looks like, you can see that here that we have a training example. We have a bag with 2 digits, 2 and 3, right? And what you observe in the bag, 2 images, and then we have a single bag label which sums to 5. You can see that the y = 2 and y = 3 are hidden from our view. We only have the bag label, which is 5. And then we also have some sort of operation between these sort of, the labels of these images, which is the sum operator. So this is essentially the basic setup that we operate on. Now here's the catch, right? The images are always 2 and 3, but many label guesses still make the bag sum to 5. So there's also 4 + 1 that can get us to 5, and 0 + 5 is also 5. But in these cases, since the images are 2 and 3, our verdict or the prediction would be wrong in these instances, right? So then, because of these sort of issues, there's also this aspect of reasoning shortcut, which is very much a popular terminology in Neuro-symbolic AI these days, coming out from the Trento group, which is, also plays a big relevance in this aspect here. Now, further, let's look at, to formalize this, we will borrow from inductive logic programming, a paradigm, which is in this paradigm, what we do is we induce a logic program, a set of clauses from examples in the background knowledge, and describe the problem with 3 different predicates, right? So essentially what we're doing is, on top of the weak supervision setup underneath, we are building a CP, TP, OP predicates on top. As a result, the relational kind of workings of these predicates give us a lens into the MIPLL underneath. So here is the picture that shows us how the IOP sort of structures the problem. At the top is the OP, which we observe, the observed predicate, and that observation must be reproduced by the conjunction of CP, the neural perception, and the TP, the symbolic symbolic transition here. At the bottom is at the bottom of this is sorry. At the bottom of this is what is, searched in this instance here. Search versus what is fixed. We search over the hypothesis, the classifier, and the operator pair, The background knowledge is also given to us, the candidate operators and the invariances, which are fixed and help us constrain the space. So essentially, the ILP searches for a classifier and operator such that CP and TP together reproduce the observed label on as many bags as possible. So here we fix one slot and infer the other, and you get the two tests. Recover the operator and recover the classifier. And this leaves us with the honest caveat. In the implementation, this search is approximated by differentiable soft, a differentiable soft marginalization, not an explicit symbolic search, because we rely on an alpha ILP system, which I'll get into later if the time allows us. Now, what does consistent mean precisely here, right? So a bag is consistent under a hypothesis exactly when the predicted labels pushed through the operator reproduce the observed bag label. Now on the left, the classifier says 2 and 3, addition gives 5, which matches, which is consistent now. On the right, it says 4 and 2, which adds to 6, not 5, inconsistent again at the level of bag. So each bag becomes a positive and negative examples here. Now the twist, unlike classical sort of IOP setup, is that this splits between, is that this split depends on the hypothesis being tested, right? So we make the whole check differentiable, soft marginalization through the operator plus a bag cross entropy. So the generator still reach the classifier. The gradient still reach the classifier. Now we have the two inductive tests here. The same framework supports two complementary questions. The scenario one is we fix a good classifier and ask which aggregation operator explains the data. That is the recovery operator TP. And in scenario two, fix a known operator and ask which per instance labels are forced. That is recovering the classifier CP. Now, IOP plays two roles throughout: a abductive role of some sort, where postulating the latent structure consistent with the weak labels, and also has a deductive one, where keeping only hypotheses that actually entail what we observed. Again, in practice, we approximate this search with a differentiable soft marginalization because we don't have a standard sort of IOP, classical IOP system that can do this sort of work. And essentially, the main piece of work we've come up with here is the semantics aspect, right? So just to give you a bit more lens into what the intermediate representation looks like, we can take a quick look, under the hood. Internally, a whole batch of bags is assembled into one constrained structure we call the intermediate representation here. Each bag contributes its classifier atoms CP, tied together by a transition predicate TP. And here are the three bags under addition: 2 and 3 to 5, 1 and 4 to 5, 6 and 2 to 8. Solving the structure, finding labels that make all sums hold, abduces the latent labels, and the bags it satisfies from the positive set. In practice, we do not hard solve it. Again, just to reiterate, we replace it with soft marginalization and a bag cross entropy loss, which conveniently upper bounds the number of inconsistent bags. There is this of a bit of a diagnostic gap metrics aspect here, where because a single accuracy number hides the shortcut, the framework reports specific measurable gaps. The bars here are illustrative of that: bag accuracy, constrained accuracy, instant accuracy. The gap between bag and the constraint tells us the bag is right, but the transition constraint TP is not really satisfied, and OP to TP shortcut. The gaps between bag and instance tells us the bag is right, but built from the wrong digits, right? Both are invisible to bag accuracy alone, and the metric most people report. But then the point is not to make the network transparent here, which is a much harder task to do here. It is to make the assumptions and failures explicit for our sake. So essentially structuring the problem so it gives us a better lens into what's happening internally. Now the failure modes depend on the operator. Which failure can even happen is decided by the algebra of the operator. Now this is a much bigger sort of formal treatment for this work. We can find that in Wang et al. And Samora et al., which I'll also link to later perhaps. But with addition, you can recover the digits cleanly, right? You just need a good classifier. With multiplication, what we see is a single zero makes the whole product collapse, a zero attractor. Once the classifier puts its mass on zero, the bag probability saturates there and the constraint loss is singular at that point. With XOR, a global relabeling preserves every bag, and the model can look onto a wrong but consistent labeling. Same data, same network, only the operator changes, and that alone decides what is recoverable. So the formal version is what we call one ambiguity and M ambiguity in the paper. Both of these terminologies further derive from the other papers that I talked about earlier, Wang et al. And Samora et al. Now the XOR collapse, having done some of these experiments with alpha ILP Shindo et al. Work, which is a visual neurosymbolic system. We test this semantics using that. What we see is the XOR is the sharpest case. And here maybe take a global relabeling, a parity flip that swaps 0 and 1 and 2 and 3 and so on. Under XOR, that flip changes no bags label. The true 2, 3 and the flipped 3, 2 both give XOR equal to 1. So every bag stays correct while every instance label is wrong. Now, instance accuracy goes to 0 while bag and constraint accuracy stay at around 0.96. Across random seeds, this is bimodal, about 0.440 plus or minus of that value. Some runs lock onto the truth, some onto the flip, and if you drop the classifier predicate entirely, it is worse. So this shows us that some scaffolding is important, but that does not solve the case. So I mean, we just with this sort of work, we're just scratching the surface right now, right? So we can see that if you drop the classifier entirely, the things get worse, as in the model satisfies bags to the operator alone, and instance accuracy falls to chance, which is 0.10 sort of value. Bag accuracy at this level does not reveal anything to us. So this may be a bit more interest once you've read the paper, which is going to come out soon, which is the camera ready phase right now. But the first of the empirical results, we have two empirical results. The first is the operator recovery. We plot per epoch the separation between the true operator and its best competitor, the difference in how many bags makes, I guess a difference in how many bags each makes consistent, positive minus negative. The true operator stays clearly above the alternatives. The shaded band is the shaded band is exactly the gap the ILP objective is maximizing here. So the takeaway is symbolic structure makes the correct hypothesis identifiable from weak labels alone. So now this gets us to another empirical result, which has to do with robustness to label noise. The second result is, I guess, here we corrupt the weak labels and watch consistency over 10 seeds. The pattern is a plateau, then a cliff, right? You see that a structure tolerates noise up to a point and then breaks sharply. The multiplication is empirically the most noise tolerant, is what we see here. Maybe perhaps the plausible explanation, though not predicted by the theory, is that it's large zero pre-image observes corrupted labels. And the theory gives structural language for the symmetry, but then does not formally predict noise tolerance. So essentially, this is a controlled study only, right? Not a benchmark sort of comparison here. So what are the takeaways from weak supervision? To sum up the learning side, we can give weak supervision a logical formal semantics on 3 predicates basis. Perhaps there could also be other works that could do something better with different other flavors of ILP. Here we just have a very basic formalism. We try it on a visual ILP system, on top of a visual ILP system. This opens up a new direction, I would say, to look into various other nuances where how weak supervision can be scaffolded in better ways with other ILP techniques. Specifically, ILP is a huge field with 30 plus years of progress. So it's definitely worth a look into future works. Tying back to the thesis, the thesis of the talk here, well, when labels are ambiguous, the constraint says which latent assignments are admissible, distinguishing genuine success from success by coincidence. So essentially, for the formal learnability treatment, I will point you to the actual works of Wang et al. And Samar et al. Wang et al. On learnability and Samar et al. On class-specific risk. Now we will move on to the generative modeling side. Just to quickly recap the problem space we're dealing with. Generative adversarial networks. A quick reminder of how GAN works. In 3 parts, we have the generator that turns noise into a sample, and the discriminator, which tries to tell real from fake, and the adversarial game between them. So the generator tries to fool the discriminator, and the discriminator tries to catch fakes, and at balance, balance the generator matches the data distribution. This is essentially a mini-max objective that I've kind of shown you briefly on the slide. In practice, we use the label smoothed non-saturating version for stable gradients. But the idea here is to produce sample indistinguishable from real data, right? So why GANs need logic? There are previous other works of trying logic to constrain GAN in various different ways. Why add logic in a specific case? Because GAN only matches the data distribution. Any rule the data obey are captured implicitly through its effect on the statistics. The discriminator catches a violation only insofar as it changes those statistics. So a fake that breaks a rule, but otherwise looks like real data is hard to reject here. As a result, a sample can be visually plausible, yet break on exact domain rule, right? So with no explicit pressure from the adversarial loss to fix it. And if we look at the real scientific data, which must obey exact rules, we have the kinetic, the kinetic energy equals 1/2 the mv squared. Molecular gap relation here, LUMO minus HOMO. The diamond cataract to volume relation. These are just some of the data sets we'll be looking into later, just taken from them. So standard training has no explicit mechanism to reinforce them. Now, just to give a quick recap into how LTN works, LTN gives us this mechanism here for us. We can write a rule once as a first order formula over the generated samples. Each predicate is grounded as a function returning a truth value between 0 and 1. For an exact identity with residual R, we use a Lorentzian function shown on the right here, with one, with truth 1 when the residual is 0 and falling off as it deviates. The connectives are differentiable. The product T norm means end is just multiplication, so gradients reach both conjuncts, and for all becomes a smooth penalty on violations. So aggregate over everything, and you get a satisfaction score between 0 and 1. The logic loss is 1 minus that score, right? That's essentially what's going on here. So now let's move on to some of the examples here. Here is what these rules look like concretely in physics. For all the samples, the duration of the kinetic energy minus 1/2 mv squared. So truth is 1 exactly when energy is consistent. For diamonds, cataract minus the volume relation. For molecules, gap equals the LUMO minus HOMO. Each is one differentiable axiom over the generated sample. When several rules apply at once, as in our MNIST denoising task, we couple them with one axiom rather than summing separate losses. The output should be clean, the same data class crisped. Reconstruct this specific input. Coupling matters. And for this, I'll come back to this in a minute. So here, just to clarify what this looks like, logic as loss, we add this rule satisfaction term directly into the generator's objective. Since this is from the first paper we have for ICLP, we only tried it on the generator. In the follow-up works, we've also tried it on generator. So I guess now at this point, I'll have to say that the one only on the generator side is now named as the LTN-GAN, just to differentiate it from the version where we apply this sort of thing to both generator and discriminator, which is the LTN-GAN. And just last night, that's why I might look a bit tired today, is submitting to NESI. We also have another work, which I'll kind of just touch on at the end of this section. But for now, let's think of G and LTN-GAN here. The logic loss is high when samples violate the knowledge base and 0 when they satisfy it. So one practical point here is we use a curriculum ramping the logic loss up over training and annealing the predicate sharpness from soft to crisp, so the model gets broad guidance first and a sharp constraint later. There are no paired rule labels and no discrete search. Here, the rule is evaluated in the same gradient step as the adversarial loss. Now, the architecture, this is just how the data flows here. Noise goes into the generator, which produces a sample. The discriminator judges real versus fake as usual. The new piece is the LTN module here, which takes the generated sample and computes a rule truth value. Now, in the original LTN-GAN, the green path, the logic signal penalizes only the generator, as I said. And in the GD, we have it both on the generator and the discriminator side. The summing up of both of these sides, we're planning to submit it to a journal soon, where we will also have a LTN-GAN in the paper, so watch out for that later. Our constraint-aware discriminator here is the original LTN-GAN constrains only the generator, as I said. and the GD-LTN-GAN closes the loop on both sides, right? So we weigh the discriminators loss on each fake by 1 plus lambda d times 1 minus its satisfaction score SI. So rule violating fakes are up weighted, so the discriminator is pushed to penalize them harder. It learns to treat a constraint violation as evidence of a fake here. So it becomes more robust, this kind of work, right? So just as a, I guess, a sanity check here, setting lambda d to 0 recovers the original generator-only model, and setting the logic weight to 0 recovers a plain GAN. So in this kind of setup, the GD-LTN-GAN is a strict superset of configurations, though, to be honest, in some cases you'll see that this sort of improvement, I guess this sort of superset is not always a strict improvement here. So this gets us to the synthetic 2D kind of setup we work on, just to show how this works. We start with a controlled sanity check, generate 2-dimensional points to match a target shape with one logical rule per data set. Sorry, just need to take a water break here. So as I was saying, if you look in the Gaussian side of things, if you just we want to stay in the box with the unit variance, and notably we just want to match the clean distribution. And in the grid, you see we want to stay in the grid centers, cover all 4 grids where we can apply for all, and there exists a for each point. And for ring, we want to generate the points in a balanced way, and I guess while avoiding the empty gap between those 2 concentric circles. So in each of these cases, the rule that we specify becomes a fuzzy truth, and the logic loss penalizes points that violate it, right? So for the result 1, let's quickly look at a plain GAN forms the rings only intermittently, adherence to 0.59 with large variance, then collapsing into a single ring as on the left. The GLTN-GAN gets almost perfect adherence, 1 with 0 variance across all 10 seeds. So we see that the rule that we passed on to the generator is now being satisfied well by the generator now. And on the grid, the cluster score goes from 0.22 to edit on the Gaussian. The covariance here against the clean target drops significantly from 0.25 to 0.18. And the headline is not just high numbers, which is what I want to point out here. It is reliability. The logic turns an unreliable outcome into a consistent one, right? So we further look at MNIST denoising. We start with a real perceptual task, which is to denoise the corrupted MNIST digits with the compound axiom on the generator. It's a different sort of task than the previous ones. The key comparison is how you combine the rules here, and the end coupling them in one axiom beats summing separate losses is what we want to show here, right? So lower error on 10 of 10 paired seeds, and below even direct clean target supervision, which is at 39% improvement. And the other lesson here, I mean, so I guess the learning here from this kind of work is that you need to, I guess you need at least one input conditional predicate here in order to reconstruct this input, or or I guess the model can collapse to one canonical sort of output that that's what we see here. And so on, we go on to the result 3 here, which is a bit more nuanced. If you see that we have direct benefits now with GLTN-GAN versus GDLTN-GAN. Oh, sorry, there's a typo here. It should have been the GLTN-GAN and GDLTN-GAN, not just GLTN and GDLTN. But you get the point. We see the outputs here with the GDLTN-GAN. We see substantial improvement compared to just applying this sort of LTN-based mechanism in the LTN, just the generative side. But what is the case with the QM9 dataset, right? So this was the kind of work that I was referring to earlier. This also sort of matters what sort of data sets we are in the domain we're applying this on. So when we tried this kind of approach on QM9, instead of helping, it helped, but not by not much margin, right? So then the question for I guess the kind of arises, and we kind of look into this in more detail. What is going on with QM9 sort of cases? This is just a submission we had submitted yesterday but if this comes out, let's hope for the best. I guess a title for the paper would still be generating the chart, not on the boundary. So I want you to keep this in mind for another time. Now, when the discriminator side helps is only when the per sample satisfaction scores vary across the batch. If every sample scores are about the same, the weighing has nothing to push on and has no effect. This is what the QM9 was showing us. The credit also splits differently by domain. On FISSIM, the discriminator weighing derives most of the gain, with a generator-only logic loss giving just a 6% benefit. On diamonds, both contribute, right? So we have the generator somewhat more, and I guess giving us a bit more. So then the practical rule here is check that the satisfaction scores are variance before turning the discriminator kind of weighing on. So that's what we want to take away here. And then the negative result, for which I'll suggest you look into for paper that's coming up later. Now, I think we're around the 45-minute mark here. So let me quickly do this takeaway slide for modeling. I guess generative modeling here. Logic as loss. Bias is again towards rule-satisfying samples, largely preserving diversity and quality at tuned settings. Differentiable inductive bias on generation. GDLTN-GAN makes the differentiator constraint aware, a new mechanism that contains the original as a special case. And the design principles here we've kind of taken away are the end couple multiple predicates rather than summing them. Include at least one input conditional predicate, introduce the logic gradually, and so on. And for the follow-up work, which FSG LTN-GAN, what we will be, just as a teaser, I'd like to lay it out that we're looking into FSG LTN-GAN, where we do the function symbol grounding and what that allows us to do in data sets like QM9. So just a quick synthesis, just a comparison of these two settings, the weak supervision, what's under specified, latent instance labels, generative modeling, which samples are admissible, and the key limitations still stay, and there's future works to kind of focus on this as well. So the broader implications this kind of leaves us with is logical constraints give us reliability and ability to diagnose, where accuracy alone is uninformative in our situations. This does not make the neural network transparent, so there could be this kind of misassumption as to what we're doing here, but slightly different. We only want to make the failure modes explicit per se, and the same thing applies to both interpreting weak supervision and controlling generation, since both constrain some kind of hypothesis space. And then there's much more future work to be done here. One of them is the shared direction forward. Could be most of the constraints here, we handcrafted them and inputted them into the systems. but essentially being able to come up with the kind of, I guess, being able to naturally learn it could open up a new paradigm within your symbolic. I mean, it already has, and I think people are looking into it, especially for these two specific cases I laid out as also future works that we should focus on. And with that, I'll conclude one last slide, and I think it's just redundant, so I'll just skip this and say thank you, and I'll open up the floor for some questions. Thank you.
Thank you, Nijesh. Olga, any questions from the audience?
Yes, there is a couple of questions, but before this, I would like to thank you, Nijesh, for making it today. We didn't know you had a submission yesterday, and yeah, really appreciate your effort and time for making it today for us. Okay, a couple of questions. How do you think ILP would be possible without a complete set of template formula patterns?
So that's for the weak supervision setup?
I think so.
So in the weak supervision setup, so essentially what we do is we do not have because it's a differentiable IOP, right? We're kind of testing this on. So the semantics is already, there is this aspect of learnability embedded in it. So I'm not sure if the question sort of, I'm a bit confused as to the templating aspect they're kind of pointing at. But in general, there's different flavors to ILP2 that we can work off of, right? So if there's no sort of the possibility for top-down or bottom-up searches, we can always look into the meta-level search possibility, which is also very kind of well-defined field in ILP. I don't know if this is what the question was referring to.
Mm-hmm. Okay, thank you. If not, we'll ask as a person who asked the question to clarify. But okay, the next question is this kind of ILP, for example, a LTN, restricted to a fixed set of atoms? That is, would it be possible to introduce atomic entities at some later stage?
So I'm still confused by the question because it's asking about LTN and ILP, is it?
It is. Okay, let me repeat the question.
Okay, yeah.
Is this kind of ILP, for example, LTN, restricted to a fixed set of atoms? That is, would it be possible to introduce atomic entities at some later stage?
Oh, yes. So that's the idea. I mean, if we carry this work forward, it would be really cool to be get to a domain where things become non-monotonic per se, right? Because right now we're operating off of the assumptions we start with, we end with that sort of, I guess, in the hypothesis-based search. But I guess along the way, if we were to input something and still be able to incorporate in the learning process, that makes it more non-monotonic. So that would be a kind of the holy grail if possible, but I'm not very sure how to do it yet.
Okay, thank you. The next question is, provided your goal is to generate a rule set, which is to depict some aspects of reality, how would the system decide between an exception, which has to be incorporated, and mere noise?
Right. I think it is a very kind of volumetric question. And some of it, so I guess that's what the kind of nuances that we presented here talk about, right? As in the ambiguity aspect and so on. So there's also this aspect of reasoning shortcut that plays into this hypothesis search process. And in some places, the nature of the input and the operator being used in a multi-instance kind of setup naturally helps us constrain those. But in some other cases, like XOR, there are less kind of constraints underneath. So as a result of that, the hypothesis search needs more guidance. And that is the kind of point of kind of the failure that we see here too. So I think this is a very volumetric question that could itself become a much bigger research statement in general. I do not have a direct answer for it, but somewhat there, right? So, but it does play a role, as in the ambiguity versus the noise and like the structure we're providing, they all mix together in the hypothesis search process. So it gets more complicated in that setup.
Thank you. And another comment question following up the first question. So let me remind you the first question. So the first question was, how do you think ILP would be possible without a complete set of template formulae patterns? And a follow-up comment, meta level could be a solution, a basic alphabet of subformulae which could be combined?
That could be the solution, but it would require, so the kind of the ILP kind of setup it's here is very much based on the I guess the visual ILP work by Shindo et al, right? So I'm basically building on top of that. But if we go a different route where we have a differentiable ILP which can do meta level work, it would be interesting to try out the semantics or kind of come up with another semantic specifically for that. That would release off of the templating at the level of kind of the question asks about, so that would be a very interesting future work.
Thank you. Okay, let me quickly check YouTube. Yes, we have a couple more questions from YouTube. I'm not sure about which particular moment in your presentation it was. You would have to retrain the network with more input variables, right? Maybe this person can comment on like what it was about. Let me read the next question. If a new instance of a predicate or a new predicate appears in the environment, the neural net has to be retrained, right?
Yes. So I guess that's how the LTN sort of setup works, right? So once we freeze the model, it's based on those predicates that were inputted during the training process. So obviously, I think that could be another work in terms of LTN itself. Logic Tensor Networks is, can an LTN do this in a dynamic way, in a kind of way that if it kind of comes up with new, I guess it kind of, come across new predicates, it literally is able to dynamically input it into the system. But I mean, all of these are kind of like much more far off from the work I have done here, because essentially what I've done is used LTN as the setup as it is now, and then just inputted it into the GAN setup to see where it benefits us, where to input it, I guess in the generative versus the discriminator, and so on, right? So, yeah.
Okay, thank you very much. These are all the questions from the audience that I can see for now. And since we have hard stop in 5 minutes, Alex, do you have any questions or comments from your end?
Yeah, just a few quick ones. Maybe some of the questions from the audience touched on this, but you mentioned gradual introduction of logic in your summary or synthesis. Do you want to elaborate a little bit on that?
Sorry, could you say
gradual introduction of logic.
Yes. So in the follow-up works, essentially the one we just submitted yesterday and so on, we've looked at what aspect of the predicate or the predicate design is in the way we do it, instead of just giving the, I guess, trying to constrain the entire generation process at once, or I guess in the same way, trying to reintroduce this sort of ILP-based formalism with everything as once, we do it in an iterative manner. So and then also there's this matter, I guess, this point of weightage-based kind of stuff, right? So whichever things the generation process fails to incorporate into the logic, now in the next iteration gets weighted more. So as a result, that would have to be respected in the second round of iteration, and so on. But these would look two different ways for ILP kind of setup and the, I guess, the LTN-GAN setup.
Got it. I wonder, I mean, you're using some of these standard VQA type, data sets, but and they have, some fixed number of examples, but have you tried to see if, because the introduction of constraints could in principle lower your need for samples. Have you played with that at all?
Not so much. All of these, I would say, I'm kind of reserved for future works. Yeah, that's
okay. Very good. I have a bunch of questions. Maybe we'll do them another time, but one other quick one. Why the Lorentzian?
So I guess this was part of, where was it?
At the very beginning.
Is it the I guess LTN-GAN setup?
Yeah, when you're, yeah, I think when you're talking about introduction of logical constraints. Near here. Yeah, there.
Oh, yeah. So I guess this I cannot readily answer as of now because I'm a bit hazy on this detail, but I would say this has differed for maybe perhaps later I could look back and get back to you on this.
It's possibly minor, but that's okay. Okay, great. Well, great stuff. Just zooming out a little bit, I want to say we look for many things when we curate, and now there's a lot more to curate from, which is great. That's the direction we were hoping for. And in the field of AI is more work on neuro-symbolic AI. And we're seeing it across arguably every conference now. It's at least a little bit of neuro-symbolic work. And one of the key, we look for particularly foundational stuff in it, where symbolic meets learning, and kind of in more broadly, but in particular in the actual mechanism of learning. This is where we think a lot more work is needed. So I'm really glad to see this work, Nijesh, and encourage further development. And for everyone else, I think this is kind of getting at the crux. This is the region of the the synthesis needed to me. So, and just more broadly, let me we'll be having be highlighting things of that general nature and beyond in the summer school. So and things that are particularly fundamental, and we so we've got a big lineup for you, drawing across literally we've looked over 50 top conferences in AI and well beyond AI to find the best, and this is generally what ends up in the summer school. So make sure you sign up. We sent out on the mailing list today. How you sign up, if you're not on the mailing list, that's the bigger problem. Get on the mailing list. All right, and thanks again, Nijesh, and see you all on the mailing list if you're not on it. Take care, everyone.
Thank you so much.